On the path towards developing confounding robust methods for estimating heterogeneous treatment effects, the first thing we need to do is review how to estimate constant treatment effects in a confounding robust way. To see why this matters, it's helpful to think in terms of a concrete algorithm. Suppose you wanted to develop a tree-based method for treatment effect estimation that's confounding robust. Well, then remember, how do trees work? Trees are first going to cut your feature space, your X space, into leaves, and then in each leaf, you can estimate a constant treatment effect. The immediate implication of this is that if you want a confounding robust tree for treatment effect estimation, you're going to have access to a confounding robust method for estimating constant treatment effects, and then that's the thing you're going to want to deploy in each leaf. So this is going to be the focus of this part of the lecture. In order to kind of get some grounding and be able to develop formal results, I'm going to make a pretty drastic assumption here. That is, I'm literally going to assume constant treatment effects. That is, for every unit, there's a treated and a control potential outcome, and that these potential outcomes are separated by the same amount for every person. For every person, there's a reward you would have gotten with treatment minus the reward you would have gotten without treatment, and that difference is tau, constant for every unit. And what we want to do is we want to estimate this tau. Next, we're going to this is a very strict setting, but the methods we're going to develop motivated by this question are going to be applicable for treatment heterogeneity also. I should also note, just in terms of notions we've encountered in the lecture so far, we've seen the conditional average, we've spent a lot of time talking about the conditional average treatment effect function, tau of x. And of course, if treatment effects are constant, then this means that the conditional average treatment effect function, tau of x, is just constant tau for each value of x. And actually, kind of for estimating purposes, this is what we're actually going to use to motivate our approach, not this stronger assumption here. I'm going to say more about this later. We've talked a lot about average treatment effect estimation. Estimating constant treatment effects is a different problem. It's an easier problem. Essentially, when you're estimating an average treatment effect, you let this function tau of x vary arbitrarily, and you want to kind of estimate some average over it. Whereas here, kind of, I give you an extra piece of information, that is, the treatment effect is actually constant. And you can target that. And that's going to kind of lead you to a different estimation theory. I'm going to say more about that in just a few minutes. All right. When we have this constant treatment effect model, also going to assume unconfoundedness like throughout. And what this is going to imply is that unconfoundedness plus the constant treatment effect model is going to mean that the expected value of y, conditional on both x and w, is going to be decomposed as follows. It's first the baseline effect. This is the expected control potential outcome given x. It may vary with x. And then if you treat it, your treatment effect gets bumped up by tau. That's the constant treatment effect part. And this kind of tau is the thing we want to estimate. One thing that's nice about this formulation of treatment effects in terms of this kind of partially linear model is that it's kind of, you can see exactly what's going on. You can also use it to get a nice reminder of why is estimating tau not so easy. You could, in this setting, think you could estimate tau by just taking the average of the treated units minus the average of the control units, because of course all the treated units had their outcomes bumped up by tau. But if you do so, what you're going to get is, sure, you're going to get this tau, but then you're also going to get this second bias term here, which is essentially the expected baseline effect among people who were selected into treatment versus the expected baseline effect for people who were selected into control. And if you're not in a randomized trial, this orange thing may not be zero in general. And so kind of being robust to that is why estimating tau is a non-trivial problem. So what are we going to do? This problem here that kind of is induced by the constant treatment effect model is often called a partially linear model. Why is it partially linear? Well, this term W tau looks like what you'd have in linear regression. Kind of as in linear regression, you have a treatment indicator. The treatment indicator gets a coefficient tau, and you want to estimate it. So this part is linear, but then you have also this baseline effect, how you depend on x, and that's nonlinear. If we replace this and kind of instead of mu0 of x, we just had something like x beta here. So we kind of assume that the baseline effects were linear in x. Then we'd have a linear model. What the partially linear model does is it kind of lets the way kind of the x's into the problem be non-parametric, but still preserves the linear structure on the treatment indicator. So this is the problem we want to solve. It's also often called a semi-parametric problem, just again, because this part is parametric. There's a single treatment effect parameter you want to estimate, but there's a non-parametric, what's called a nuisance term. It's a nuisance term because it's a nuisance because it's something we need to estimate, but we're not necessarily interested in it. So we have a non-parametric nuisance term, but then a parametric target. So how are we going to estimate tau? Any semi-parametric problem, essentially because it has this kind of non-parametric component, requires a little care in approaching estimation. But here, it turns out there's a very nice solution that kind of starts from what's called Robinson's transformation, introduced in this paper. And the idea is, first, let's define these auxiliary quantities. The first thing we have here is E of x, our old friend, the propensity score. Like I mentioned earlier, it was a concern that the propensity score didn't feature heavily in your STX learners because usually the propensity score plays a key role in helping you be confounding robust. So here the propensity score makes a return. We're also going to define this other quantity, which is a little less commonly used, but still easy to interpret. This is the expectation of y given x, ignoring treatment. So this is kind of my best guess of what your outcome would be if I only know your value of x, but I don't know yet where you treated or not. In the partially linear model, m of x is mu0 of x plus tau times your treatment probability. And given this notation, what you can do is you can just essentially subtract subtract m of x from both sides of this expression here. And then what you see is that y minus m of x is equal to tau times the treatment minus e of x plus epsilon. Epsilon here is really just kind of the difference between y and its expectation given x and w. The point is that we know that the expectation of epsilon given x and w is 0. In rewriting the problem in this way, we've essentially done nothing, but we still get some very helpful insights out of here. Suppose you actually knew m and you knew e. Then how would you estimate tau? Well, it's very easy. Just run a univariate linear regression where your response variable is this difference, y minus m. Your single regressor is this variable, w minus e. And then tau is just kind of the regression coefficient you get by regressing y minus m on w minus e. If you knew m and e, then this approach would give you, very simply, a consistent, asymptotically normal method for estimating tau with kind of standard inferential guarantees also. Of course, the difficulty is that unless you're in a randomized trial, you probably don't know the propensity score E, and you certainly don't know this baseline effect M. Or this kind of expectation of y given x, a best guess of y ignoring treatment function M. So you can't apply that strategy. But this still suggests a practical algorithm, right? If we know what we would do if we knew E and M, but we just don't know them, then you could hope that kind of we've got access to a number of machine learning black boxes to solve prediction problems here. This predicting W and Y from X, these are just basic prediction problems. So we could estimate E hat on M hat by throwing a predictive black box at the problem. And then we could estimate tau by residual and residual regression. If we had kind of plugged the true M and E terms in here, this would kind of, by Robinson's transformation, immediately give you a good estimate for tau. Here we're going to have to estimate the M's and E's, but you might hope that this would still work at least reasonably well. How good is it? It's not clear from writing this down, but kind of what should be immediately clear is that if M and E are consistent, then tau hat should also be consistent for the constant treatment effect parameter. Another thing I should note is this expression I wrote here. This is just the closed form solution for the kind of univariate linear regression problem here. This is kind of, this thing in purple here means nothing else than just run the univariate regression of y minus m hat on w minus e hat. All right, so we have this. It's obviously consistent. Is it good? I wouldn't be telling you about this if it weren't good. We get a very nice result on the asymptotic properties of tau hat. And this should be kind of reminiscent of the result we saw for the average treatment effect estimator using AIPW we saw in week 2. And the guarantee is as follows. The end result is what we'd want. That is a central limit theorem for the constant treatment effect with errors that decay as 1 over root n. That means when we take the errors and we blow them up by root n, then we get a kind of limiting normal random variable. So that's exactly what we'd want. And what are the conditions? The conditions are, again, that these m hat and e hat estimators, well, they don't need to be perfect, but they need to be reasonably accurate, but they don't need to be kind of 1 over root n scale accurate. So kind of like I emphasized in week 2, whenever you're using machine learning methods for causal inference, it's okay to assume that they're pretty accurate, but you should never assume that they're perfect. And this guarantee here is exactly the kind of thing we'd like, which is in steps 1 and 2, when we kind of through machine learning black boxes at the problem of estimating E hat, M hat, we need them to succeed in being reasonably accurate, but not necessarily perfect. And again, just, I know I've emphasized this a lot, but to kind of emphasize the counterintuitiveness of the result, you might think that there's this kind of garbage in, garbage out principle, where if you have to estimate E hat on M hat terms, well, if there's kind of some error scale on these M hat and E hats, then there's no way tau hat could be more accurate than kind of these estimated things for M hat and E hat you're putting into the expression. But this theorem tells you that the garbage in, garbage out principle doesn't hold here. You're allowed to have kind of estimates here whose typical errors are on the order of 1/4 root n. So that's a pretty big error scale. And yet, just like with the AIPW estimator, the errors are going to cancel out in just the right way. So actually, even though these might have 4th root n scale errors, 1/4 root n scale errors, this will be accurate on the 1 over root n scale. So it'll be an order of magnitude more accurate. In terms of details, the conditions are essentially the same as what we had for AIPW, which is here. I said you needed some modest regularity conditions. What are those regularity conditions? Well, it turns out just kind of, as long as you use cross-fitting, you can essentially ignore any regularity conditions that go in there. So the setup's essentially going to need to be, you run this estimator, get M hat, E hat, use cross-fitting, like in week 2, and then as long as M hat and E hat are reasonably accurate, you're going to get the central limit theorem you want for tau hat. And I'm not going to talk about it now, but kind of you can get confidence intervals for tau out of this residual and residual regression the way you'd usually get confidence intervals out of a regression of this type. The theorem essentially tells you that you can ignore any, as long as you use cross-fitting, you can ignore the sampling error of m hat and e hat in building confidence intervals when the conditions of the theorem hold. And that gives you a kind of very simple way of constructing confidence intervals. So a last thing, this is kind of an aside, but just to kind of connect some dots. If you think this kind of way of estimating a constant treatment effect is a little bit strange or unusual, I just kind of to try to convince you that it's not. I just wanted to connect it to an estimator that hopefully is familiar, and that is the linear regression, the kind of standard linear regression estimator for the treatment effect, where kind of what you do is you just run linear regression, yi kind of tilde xi plus wi. So this is kind of an R notation. You just predict y as a linear function of x and w, and grab the coefficient of w as your treatment effect estimate. And if you've taken a kind of linear algebra-based class on linear regression, you'll probably know that there's this following equivalent characterization of linear regression, which is to estimate the coefficient of w on y in a model where you control for x. Well, you can kind of construct that coefficient as follows. First, fit a linear model of w on x, then fit a linear model of y on x, and then the coefficient for w in the full regression, where you predict y from x and w, is gonna involve running a residual on residual regression, where you kind of regress regression residuals of y versus your best prediction of y from x, versus those on w versus your best prediction of w from x. And so what this actually shows is that, at least algorithmically, linear regression is just a special case of this kind of estimator based on Robinson's transformation, where we've, instead of using machine learning methods for e hat and m hat, we just use linear regression to predict y from x and w from x. So there's a lot to say about this connection and kind of many lenses under which you could investigate it. But at the very least, I hope this connection suggests that this estimator based on Robinson's transformation is a very natural way to kind of move beyond linear regression, at least in a setting where you want to kind of preserve the constant treatment effect assumption. So you still have something that's like a constant treatment effect parameter that you could hope to target using something that's like a generalization of linear regression. So this is how how one can estimate constant treatment effects in a way that's confounding robust under the kind of no unmeasured confounders assumption. In my experience, it's a very good estimator. It's one I recommend using. And just kind of the bigger picture is that now we've seen two different confounding robust estimators. This means the AIPW estimator we saw in week 2, and the residual and residual regression estimator based on Robinson's transformation for the constant treatment effect. And both of these estimators had very similar properties where we were working under the unconfoundedness or no unmeasured confounders assumption. Then we ended up in this kind of semi-parametric type specification where we have kind of a low dimensional object of interest, either the average treatment effect or the constant treatment effect parameter. And we also have non-parametric nuisance components, the baseline effect, the propensity score. And then what the shared property of these estimators is that they kind of start with machine learning based estimates of the nuisance components. And as long as they're reasonably accurate, then you get a 1/√n rate central limit theorem for the thing we actually care about, our target. So that's all I'm going to say here, other than kind of recommending the use of both estimators. For those of you who want to dig deeper, I should emphasize this. Both are a case of a much more general recipe. If you want to read more about it, this paper here. by Chernyshukov and co-authors has kind of much more to say about how and why these kinds of estimators with these kinds of properties arise. All right, the last thing I wanted to say about estimating constant treatment effects, and this is a little more of an aside, but I just kind of, some of you may be confused. We talk about estimating average treatment effects. We talk about estimating constant treatment effects. What's up with that? They seem like very similar estimates, very similar problems. Why is there a difference? And to see why there's a difference, consider a problem where kind of you have a fairly large X space, and then you have some regions of X space where it's very easy to estimate treatment effects. Say kind of you have good balance across treated and control units, you have many units of both types. And then you have another region of X space where it's very hard to estimate treatment effects. Maybe kind of almost everyone was assigned to control, so you barely have overlap. Well, in that kind of setting, estimating a constant treatment effect versus an average treatment effect are going to end up being very different problems. If you want to estimate an average treatment effect, well, what do you essentially have to do? You need to estimate the treatment effect here, where it was easy. You need to estimate the treatment effect here, where it's difficult, and then kind of take the average of the two treatment effects. And if over here your treatment effect estimates were inaccurate, there's kind of nothing you can do about it. Your treatment effects are going to be inaccurate everywhere. On the other hand, if I tell you a priori that treatment effects are constant everywhere, well, you can just kind of ignore this part of feature space where the problem was too hard and just kind of estimate your constant treatment effect over here, where you've actually had good signal, and then just extrapolate that everywhere. And that makes the problem a lot nicer. So to kind of see this play out in an example, here's a simple simulation. The salient part here is that first, the treatment effect is constant. It's everywhere 0.3. So if you know that the treatment effect is constant, you can just kind of run methods for constant treatment effects. But maybe if you don't know that the treatment effect is constant everywhere, then you'd kind of, and you wanted to estimate an average treatment effect, then you'd do something else. And why is kind of this problem harder when you don't know that the treatment effect is constant and you have to kind of estimate treatment effects everywhere and aggregate them? You can see this by essentially cutting the problem into 3 zones based on the propensity score. So here, the propensity score is here. It depends on X3. There are some units. There's one group of units who the propensity score is very small. Most of these people receive control. There's some region of feature space where most people get treated. The propensity scores are close to 1. And here's this in-between zone where propensity scores are far from both 0 and 1. This is kind of a region with good overlap. This is kind of the type of data we like for estimating treatment effects. So if you wanted to estimate an average treatment effect, what would happen? You'd kind of qualitatively have to separately estimate treatment effects in these 3 zones. Here, estimating a treatment effect is very hard. Almost everyone gets control. You have hardly any treated units, so you just have very little information about what the treatment effect actually is. This middle zone, you have good overlap. So estimating a treatment effect is easy. And again, here, it's going to be hard again because most people receive treatment, so there are very few controls. And then with the average treatment effect, approach is going to have to do is then kind of aggregate 2 mostly kind of treatment effect estimators for these 2 regions where estimating treatment effects was hard. And so probably those treatment effect estimates are going to be pretty inaccurate, with kind of the more accurate one from this easy zone, but then kind of any inaccuracies you built up in the difficult zones are going to add up. On the other hand, if you're estimating a constant treatment effect, you just kind of don't care about these 2 zones. You effectively throw this data away. You just kind of only zoom in on the part of the data set where you had good overlap and where you can estimate treatment effects accurately. You learn what the treatment effect is there, and you're just done. You don't worry about the rest of the problem. This is, of course, a qualitative story for what the methods do, but in practice, it isn't the intuition goes through for what actually happens also. And okay, what do the numbers look like? So here, as always, I kind of just gave you a little bit of code. You can copy paste. This implements the constant treatment effect estimator by residual regression with heterogeneity, robust standard errors. And if you do this, you get, remember the true constant treatment effect here was 0.3. Your 95% confidence interval is 0.3 plus or minus 0.15. This is very good. What about if you didn't know a priori that your treatment effect was constant? So you kind of had to use a method for average treatment effect estimation that aggregates data from everywhere, including the difficult zones, and then try to synthesize. Well, the treatment effect you get out of this is going to be much less accurate. Here we got 0.56 plus or minus 0.35. The point estimate was less accurate and the confidence intervals were wider. And this just kind of highlights the extent to which the problem of average treatment effect estimation is harder than the problem of constant treatment effect estimation. For those of you kind of thinking of problems in terms of the kind of applications, you might be sensitive to the tension here, right? Kind of in this problem, the treatment effects actually were constant. But kind of as an analyst, you had two strategies. You could either assume that the treatment effects were constant, kind of assert knowledge from theory, but without validating it from data. And if you're willing to assert constant treatment effects, then you can kind of estimate the constant treatment effect very accurately. Or you could kind of take a more agnostic approach where you don't start by assuming that treatment effects are constant. You allow for heterogeneity, and then you want to estimate an average of this tau of x function in a way that's more robust. And you might like doing this because it doesn't require asserting that treatment effects are constant a priori. But here you see that there's kind of a large cost in precision from doing so. Yeah, it's kind of a tricky trade-off. If you're interested in this trade-off, then kind of one very important thing to ask is, what happens if you think the treatment effect is constant? So you kind of run our residual estimator for the constant treatment effect, but actually there's treatment heterogeneity. So kind of there doesn't exist a thing that should be called the treatment effect parameter. So if you just run this estimator that was justified under the setting of constant treatment effect in a setting where tau of x is not constant, what do you get? And the thing you end up getting, it's actually very nice. If you assume a constant treatment effect, but there's actually heterogeneity, then what the constant treatment effect estimator is going to converge to is this thing I called here tau e, which is a weighted version of the average treatment effect, where kind of different parts of feature space are weighted by e of x times 1 minus e of x. That is kind of regions of feature space with more propensity scores that are further kind of nicely between 0 and 1 are given more weight, and with regions where propensity scores get very close to 0 and 1 are given less weight. And actually you can check that among all weighted average treatment effects, this tau e is the weighted average treatment effect that you can estimate with the best precision under kind of a homoscedastic model with this propensity score. So anyways, if you're interested in this stuff, this is kind of a rabbit hole one can go very far into, but the point is that there, in the literature, you can think of two ways to justify Robinson's method. It can either be a method that kind of takes this treatment effect, the treatment effect is constant assumption very literally, and then just tries to estimate that tau in an efficient way. Or you could relax. You could say you essentially think that the treatment effects are almost constant, and given these assumptions, you're going to run this method. You recognize that there's some heterogeneity in the treatment effect, and the thing you're going to get is actually a weighted average of the treatment effect. But if the treatment effects are close enough to being constant, then maybe this weighted treatment effect is close enough to what you care about. And you can just relax and use that estimator in your analysis.